Hello, you'd think that after the final experiment, Flat Earth would have gone back into obscurity with a whimper, but once again I bring another Flat Earther showing incredulity and fundamental lack of understanding. Several months ago I was scrolling on the platform formerly known as Twitter when a discussion thread popped up once again talking about selenelions. With atmospheric refraction being a thing, I never really gave it much attention, but somewhere in the thread, someone brought up observer latitude, which piqued my interest. It wasn't a new revelation, but once again, there was an aspect of the phenomenon I did not consider until latitude was brought up. The location and duration of the selenelion reminded me of my breakdown video of Spacebuster's Scamtarctica video. In that other video, I showed how very small and subtle changes in the sun's declination could cause dramatic changes in sunrise and sunset times closer to the polar regions. So, when it came to selenelions, I wasn't particularly interested in exploring them before, but the posts back and forth in the social media thread resonated and connected with my earlier video. And here I am, after a bit of research, sharing my findings. Before diving into the topic, a very brief description should be given. A selenelion is when the sun and moon both appear above the horizon during a lunar eclipse. This implies that one must be at the right place at the right time for a selenelion to be possible. So the sun and moon's right ascension during the phenomenon will ultimately matter. The point of contention comes from flat earthers who object to the possibility that both the sun and the moon can be visible above the horizon at the same time if they are supposed to be geometrically opposed on an oblate spheroid. Before throwing the proverbial baby out with the bathwater, we should use the globe model to predict what should be possible on the globe before dismissing it as impossible. So, what sort of observation window are we talking about? How long can a selenelion last? We'll get to that shortly, but we need to step back a bit and establish some geometry-driven requirements for an eclipse. The most obvious thing we have to consider about selenelions deals with where in the celestial sphere the sun and the moon are to not only create the conditions of an eclipse, but also that as one is setting, the other is rising. Without nearby clouds, the moon, specifically during the nights, can easily be determined where it is in the sky. With stars to act as a guide, we can easily resolve where it is using right ascension and declination. It's harder to obtain the sun's location since it's far too bright to have nearby stars visible. But measuring its altitude angle for one's latitude at solar noon and some math, we can get its declination. With an accurate clock, we can also determine its right ascension by determining when specific stars also cross the local meridian, the several nights before and after, using 15 degrees per hour. With the moon's ecliptic somewhere around 5 degrees off from the sun's ecliptic, full moons happen every month, but solar and lunar eclipses are far less frequent. Selenelions are even more infrequent as it happens on one's location relative to where the sun and the moon are in the sky during the eclipse. Obviously, at high noon, you can't expect to see a lunar eclipse, nor can you see the sun during an eclipse hours after the sun has set. Like the points I raised in the Scamtarctica analysis video, we need to define terms and find a common frame of reference when considering a selenelion. By tracking the moon's position relative to the surrounding stars, it becomes very easy to produce a composite image of the moon entering and exiting the Earth's shadow. And after enough observations from enough eclipses, it can be shown that up to 2.5 moons can fit within the diameter of the Earth's shadow. The moon's angular size is about 0.5 degree. So for part or all of the moon to be or to remain eclipsed, it needs to traverse the 2 moons' diameter distance worth of arc plus a little bit more. The moon's synodic period is about 29.5 days, which makes its arc about 12.2 degrees per day relative to the sun. In 1 hour, the moon arcs about a half a degree relative to the celestial sphere. So to arc the remaining up to 1 degree of totality inside the umbra, the total eclipse can last up to 2 hours. Most eclipses are more likely off-center and last less than that. The question that flat earthers need to answer is, where then does the moon have to be in the Earth's shadow to be considered an eclipse? If the sun is just rising or just setting, does the moon have to be in totality and still appear above the horizon to be considered a selenelion, or would it still be acceptable to be considered a selenelion when a partial eclipse begins or ends? Also, if you are fortunate enough to be in a specific location, the moon could just enter totality as the sun rises, or it could just exit totality just as the sun sets, which places the moon at one of the extremes within the umbra, giving the observer a few extra minutes. Keep in mind that totality can last up to 2 hours. So from a timing point of view, since the moon is not perfectly centered within the Earth's shadow, the moon could remain above the horizon for up to 4 extra minutes for totality and even longer for a partial eclipse. By answering the question of what is acceptable for an eclipse, we could extend the window of a selenelion by several minutes. The next aspect of a selenelion I want to consider is relative to the path of the sun or the moon takes when rising or setting. The sun and the moon have to be 180 degrees apart in right ascension and complementary in declination for a total eclipse to be at its maximum. If the sun is at a declination of 10.7, the moon has to be at a declination of minus 10.7. If the sun is at a right ascension of 90.35, the moon needs to be at 270.35. Spherical geometry tells us that the further north or south we go from the equator, the shallower the rise or set angle becomes for the sun or the moon. We also need to consider the declination, because at 45 degrees north latitude, a star with a declination of more than 45 degrees can never appear to sink below the horizon. Procyon at 5 degrees and 9.5 minutes may only be visible at certain times of the year, sharing the sky with the sun 6 months later. But Polaris is always visible in the northern hemisphere every cloudless night from sunset to sunrise. Alternatively, Sirius, with a declination of almost minus 16 degrees 45 minutes from Union Glacier, should, weather permitting, be visible continuously from the start to the end of the 24-hour night, a span of time that lasts for many months. From past experience, such as my earlier analysis of Scantarctica, I knew that latitude and the sun's altitude angle affects day length, and selenelions should follow a similar pattern. Not quite the same, but similar. To help me get a better understanding of that relationship, I built a spreadsheet by computing how long a given latitude should expect to see a selenelion at maximum totality for a given sun's declination. The two primary factors with the greatest effect, there are others that also contribute, but with much less effect, that determine when an object sets or rises is dependent on the observer's latitude and the object's declination. And to illustrate that relationship, I created a heat map. The map shows how the duration of a selenelion is a function of latitude and declination. If you want to explore in more detail the math I used, I'll make the spreadsheet available, so check the description. The observer's latitude is implied to be halfway between the ground position longitude of the sun and the moon. Otherwise, an asymmetry between rise of one and set of the other would occur, and the window of selenelion is smaller. The moon is also implied to be at the precise moment of the full moon. That is, the moment it transitions from waxing to waning for simplicity of calculations. The rise and set correction allows for specifying how much of the disk is visible before it's considered risen or not. Standard atmospheric refraction can also be applied, and this can show that refraction alone is not a deciding factor in the visibility of a selenelion. Observer height also plays a part in determining when objects rise or set. If you were on a beach, for example, you might have less time to observe the selenelion than if you were on the roof of a 100-story building. Fill in the cells that are in yellow and the spreadsheet will calculate how long a selenelion should last for the sun's declination at 0.5 degree intervals. To summarize, the moon's location within the umbra of the Earth's shadow plays a factor in determining when a selenelion occurs. The definition of rise and set also plays a factor. There is also one more aspect of the selenelion window I didn't talk about yet, and that is the object path taken based on declination when crossing the horizon. If you differentiate the path angle of the sun or the moon at rise or set for 0 degree declination, the angle or the complementary angle matches the zenith angle of the observer's latitude. An observer at 45 degrees north will see the sun during the equinox at sunrise move at a 45 degree angle when facing due east and minus 45 degrees when facing due west at sunset. For someone at 10 degrees north, it would be 80 degrees and minus 80 degrees. At the equator, it would be straight up or down, which is 90 and minus 90. The rise angle, however, changes more dramatically with increasing distance from 0 degree declination. The rise and set angle at 20 degrees declination is much more shallow for someone at 45 degrees north than the rise and set at minus 20 degrees declination. What this means is that if the moon is setting at 20 degrees declination for someone in the north, with the sun rising at minus 20 degrees declination, the moon will appear to veer off a little bit more to the right before it disappears from view below the horizon, when the sun will seem to pop up more vertically above the horizon before it starts veering off towards the right. This alone won't really add much appreciably to the amount of time of a selenelion. It may be a few seconds, but it is a measurable factor and it's worth considering. For a concrete example of how much time they can last, after a bit of research, there was an eclipse on November 8th, 2022, with the potential of a selenelion in North America with a duration of 9 minutes for St. Louis, Missouri. I did a screen recording of stellarium of what it should have looked like in that city, and also in my own app that I wrote to show how selenelions can work. So, how does this flat earther argument stack up to observable reality? About as well as all the other ones. Well, that's going to be it for now. Thank you for watching. If you liked the video, I would appreciate the thumbs up, the subscribe, comment below, all that other good YouTube stuff. And with that, I'm going to see you again in another video soon enough. So bye for now.